Okay, so we have another example here, and pretend I haven't written anything. So we have a rigid member, ABDE. It's supported at A by a single shear pin connection and at B by a tie rod, okay, that's attached at B and C with pins and double shear. The pins at A, B, and C each have an ultimate shear strength of 80, and the tie rod has a yield strength of 60 KSI. So we're looking at the ultimate, is that the highest stress where we're in the plastic region, and the yield, we don't want this to go beyond yielding, okay? So a concentrated load of P equals 24 kips is applied perpendicular to DE, and we're using a factor of safety. So I'm going to start with what are my givens, just like always. Let's try to organize our thoughts and our information. So we have pin A. Pin A is single shear. It has a shear ultimate stress of 80 KSI. See, I can't even copy correctly. 80 KSI. And a factor of safety of 2. So our allowable, the shear stress that we're allowed is that ultimate divided by factor of safety of 2. So we have an allowable stress of 40 KSI. I also know that my area of pin A is going to be pi over 4d squared. Okay, I can do the same thing with pin B. It is in double shear. And there we go. It is in double shear. And again, it has an ultimate of 80 KSI. So when we're looking for that allowable, it's going to be the ultimate divided by 2 is 40 KSI. We also have pi over 4d squared. Okay, now I need to go over here and look at my tie rod. My tie rod is sigma because it is normal. It is a tension member. It has normal stress. It is being stretched longitudinal. Okay, it has a yield stress, so that means we don't want to leave the elastic region, of 60 KSI, and it also has a factor of safety of 2, so our allowable stress is 30 KSI. And it's a tie rod, again, pi over 4d squared. So now we need to break this up and draw a free body diagram. Okay, at A, I have a pin, so I have X and Y components. Because this is a two-force member, I can cut it, I know it's in tension, and I can go back and look at my geometry of 6 and 9. I can divide both by 3, 2 and 3, 2, 3, square root of 13. Okay, the nice thing about knowing that it's a two-force member is I also know that as it's pulling up down here at C, that my pin forces, the X and Y components, are going to be pulling down equal and opposite. Okay, and again, when we find shear, we have to find the magnitude of the force that's acting across the pin, because these are just the X and Y components. Okay, this measures up 9 feet, 4 feet up to where we've angled. We are angling at 20 degrees, and I am told the length from D to E is 8 feet. So I'm going to have to use trig to calculate the height and the base of this triangle to finish getting the geometry of how much this force P is offset in the X direction and how much it's offset in the Y direction. So I have 8 sine 20 and 8 cosine 30. So is opposite, cosine is adjacent. I also need to break up load P because it's easier for me if I can break everything up into my XY world. And if it is perpendicular to DE, if I have an x-axis and I'm rotating up 20 degrees, then I'm also going to have my y-axis and I'm going to rotate over 20 degrees. So I'm rotating counterclockwise. And when I do that, here's my force P, but I need it in my XY world. So opposite, so opposite, so my X component is so sine. Okay. My adjacent to this 20 degrees, so ka adjacent, so ka adjacent will be the Y component. So remember, you can't just say X components are cosine and Y components are sine. You have to look at where it's being rotated from. When we found it from the height, we were being rotated from the X-axis, so it is cosine sine. when we're finding the force, it's rotated from the y-axis, so it's going to be sine cosine. Okay, so now that we have that taken care of, we can now start with equilibrium. We can go back and find these forces. I know that this is going to be 24 kips cosine 20 and 24 kips sine 20. So I do have value there. I have found my allowable stresses based on my materials up with my material properties. And we have normal. Okay. And I also know that all of these are going to be areas of pi over 4d squared. So let's start with equilibrium. Okay. If I sum forces in the x direction, I've got ax, and I have the x component of TBC, which is 2 over square root of 13. If I sum y, I have this, I have the y component, so summing x and y is still going to leave me with 2 unknown values. But I do know how the x and y components of this tension are related. So if I sum my moments about B, then I could calculate AX. If I summed my moments about A, because I know how these components are related, I would still only have one unknown, the tension in BC. Okay, so you could, if you're still struggling with summing moments, sum it about A and get the tension, okay, or sum it about B and get AX. So I'm going to start with summing about B, because why not? So if I sum it about B, okay, I have AX times 9 feet, and then we come up minus P cosine 20, and it's over 8 cosine 20, and then I'm going to have minus P sine 20, and its height up is going to be 4 plus 8 sine 20. So fx dy, fy dx. And all of this has to equal 0. Okay, so we are going to get started with our algebra. I have 9ax equals, I'm going to rotate this over and take that over so they become positive, and I have 24 cosine 20 times 8 cosine 20 plus 24 sine 20, 4 plus 8 sine 20. And when I work this out, I get AX equals 24.98 kips. I got a positive value, so I know it's in the direction that I assumed it to be. Okay, so now I can sum forces in the x direction. There's our rule. We're summing forces to the right as positive in the x direction. And I have 24.98. That's coming from my x-axis here. I have the x component of that tension, which is going to be minus 2 over square root of 13 tension BC, plus the x component of my force, 24 sine 20. All of this equals 0. When I work my math out, I'm going to isolate this. Actually, it's negative, so I will take it over to the right side, and I'll have 24.98 plus 24 sine 20 equals this, and then I'll cross multiply. So I end up with a tension in BC of 59.84 kips. And now I'm going to sum forces in the y direction. We're still going to use sum forces in the y direction equals 0. And I have minus 24 cosine 20. That's for my load. Minus, okay, the tension, it's coming down, negative, minus 59.8, okay, Okay, but we don't have the entire tension because that's going towards the left and down. So the y component is 3 over square root of 13 plus ay equals 0. And when we take both of these negatives to the other side doing algebra, we will find that ay is 72.338 kips. Okay? So we now have the x and y components of our bolted A. We have the tension in the tie rod. If we wanted to, we could go back and find the x and y components here at where we're tied into C or tied in at B. But again, the x and y components don't really matter. We'd use Pythagorean theorem, cx squared plus cy squared equals, and we get that hypotenuse. So once we know the tension, that's actually the resultant of these x and y's, and it's the largest value that we would use. So when we're looking at our pin at A, then we need to find the magnitude of that shear force at A, and that's going to be from the x squared and the y squared forces, so the shear that's occurring at A, and it's not a stress yet, it should be V, it's not a stress yet, but to find that magnitude of shear, we need to take the 24.98 kips squared plus the 72.34 kips squared, and we're going to find then that the shear at A is 76.53 kips. And see, that's larger than the y, and that's larger than the x, because it is the hypotenuse, it is the actual resultant of these two forces. Okay, I already know then the shear at B and the shear at C, those are my pins, is going to be the same thing as the tension, 8 kips, and I know that the normal force that's acting on BC is also 59.8 kips. So it's normal when it's acting perpendicular, okay? When it's acting perpendicular to the shear pin, it's that normal force that becomes, here's the cross-sectional area, it becomes shear. Okay, it's normal. We're pulling this like in a rubber band. As it passes across, it's going across the cross-section of the bolt. It becomes a shear force. So these are going to be the values that we design with. So let's look at our tie rod. Okay, stress equals P over A. And we were allowed, based on the front page, 30 KSI. I also know that the normal stress, the normal force that's acting, okay, through that is 59.8 kips. And if I keep up with my units, I can easily see how to get the inches, the cross-sectional area out of that if I don't remember how to set up the equation. I have kips, I have kip per inch squared. It's just setting up that ratio. So we have 59.8 kips divided by pi over 4 d squared equals 30 KSI. So if I do my math correctly, I'm going to cross multiply, take the square root, and the diameter of tie rod BC has to be greater than or equal to 1.594 inches. Okay, so we would 1.6 inches or larger. If I'm looking at the shear pin at A, its shear is V over A. The allowable shear stress that I found on the previous page was 40 KSI. That's what I can work with. The actual force that's acting on that pin is 76.53 kips. Pi over 4 area of pin A, okay, squared. And if I cross multiply, divide, take the square root, then I will find that the diameter of A has to be greater than or equal to 1.561 inches. So if I were looking at to the closest tenth of an inch, it would be greater than or equal to 1.6 inches. Okay, I'm not going to go smaller in that area. And then if I'm looking at the pin at B or C. It's shear, it's a pin. Okay, the allowable was 40 KSI. The shear force was 59.8 kips divided by pi over 4 d squared. And the thing to keep in mind here is it's in double shear, so we get to increase that area. Cross multiply, take the square root, and the diameter needs to be greater than or equal to 0.976 inches. So we could say greater than or equal to 0.98. And that would be the start of our design process.